Okay, part 2 of Build Your Own SQLite on CodeCrafters. Now we're dealing with step 3 in this challenge, count rows in a table. We have already seen how to sort of access the database, how to print the table names, and we did that in this file. Last time we just copied this code and made some changes to print all of these table names that were already being fetched by this code. Right. So now, what do we need to do now? Let's take a look at this third stage. We are given a query, and we need to find the number of rows in the table in that query. Actually, it does not really have to be a query. It can be anything as long as the last word in this whatever text we get is a valid table name. Because remember, we don't need to implement a full-blown SQL parser. The tester will assume, the tester will give us a query in which the last word is a valid table name. So we can just assume that whatever comes in, we'll split that on space and pick the last element, and that will be a table. And then we need to load the data from the table and print the number of rows in that table. So how do we do that? We need to read the tables row from SQLite schema table and follow the root page value to visit the page corresponding to the table. Okay, what does that mean? So it means, well, generally speaking, and just to really water it down, we know where the table is stored. We know that by looking into this first page. Where is it? Yeah. And then we have all of these table names. We have the type of the table, name of the table, and we know the root page. Root page is the position in the database file where we can go and look for the data that is stored in this table, whatever this table is, right? Let's take a look at this database file format. And I think let's just start with pages. So there is also this database header, and we'll have to look at this also, but let's start with pages first. So the main database file consists of one or more pages, right? The size of a page is a power of 2 between 512 and 65,536 inclusive, right? So both of these values. All pages within the same database are the same size. Okay. So if we can figure out the size of the page, then we can, that is going to be the size for every page in that database. And how do we figure that out? The page size for a database file is determined by the 2-byte integer located at an offset of 16 bytes from the beginning of the database file. So what it says in so many words is that just look at the 16th byte from top, from the beginning of the database file, and read 2-byte integer, and that is your page size, right? Pages are numbered beginning with 1. So if our page size is, say, 1024, and we need to look at, we want to read from page 4, then we'll just seek to 4096, and that guarantees that we'll land upon page 4 because of this computation, the way things are stored. Then the maximum page number is this, minimum page size is 512 byte, the maximum size is this. I think all of this information is necessary if you're trying to build full-blown SQLite, if you're trying to handle all cases, if you're trying to be compatible with everything. Right now, we are not trying to do that. We just need the page size. We need to figure out how to read the page size. Then once we have the page size, then we just need to hop between pages. That is all. Usually, SQLite will hit the maximum file size limit of the underlying file system or disk hardware long before it hits its own internal size limit. Well, that makes sense. In common use, SQLite databases tend to range in size from few kilobytes to, or let's see if there is any more usable information. At any point in time, every page in the main database has single use. Okay, so there can be a lock byte page, there can be a free list page, there can be a B tree page, and B tree can then be an index or a table. Then a table and an index page both can be either an interior page or a leaf page. Then we have payload overflow page and a pointer map page. We'll come to all of these. Right now, I think we only need to worry about a B tree page and yeah, I guess just generally speaking, B tree page because well, I think we'll cover all four of these: the index B tree, index leaf, table interior, table leaf. Sorry, index interior, not index B tree. Then there is some information about read and write. I think all reads from and writes to the main database file begin at a page boundary, and all writes are an integer number of pages in size. Reads are also usually an integer number of pages in size, with one exception that when the database is first opened, the first 100 bytes of the database file are read as a sub-page size unit. All right, so what does that mean? I think that means that the first page in the database also includes the database header, right? So database header, page header, and then page content. I think that is true for the first page, and then rest of the pages are all just page header and the page content. Then there is some information about modifying the databases. Modifying the pages, not databases. And this is the database header table. So we have first 100 bytes, and this is how they're arranged. First 16 bytes are just this header string, SQLite format 3, and then null byte. Then at offset 16, we have these 2 bytes are database page size in byte, must be a power of 2 between 512 and 32,700. Hold on, wasn't this? The size of a page is a power of 2 between 512 and 65,536 inclusive. Must be power of 2 between 512 and 32,768 inclusive, or the value 1 representing a page size of, oh, okay, so that just double of that, right? Cool, that makes sense. And a bunch of other information. I think we can parse this database header, but really the only thing that we are going to need from this is these 2 bytes at offset 16. That is all we care about right now. All right, so we are going to parse this database header, figure out the page size, and then we can find the root page from this table. So let's say root page is, I know, 3, 4. We'll multiply that by the page size and we'll get an offset. We'll then seek to that offset, and then we'll find the page header at that position. We'll parse that, and there'll be some data that we'll need to parse, right? So those are the broad strokes, and we can I think start making changes. Actually, before we do that, let's do one thing. Let's go ahead and take a look at the database file that we have. How do we do that? Okay, let's do it this way. So I got this hex editor, and I have my database file. Where is it? Sample.db. Right, so this is my database file, and you can already see it has, something. You can make out a couple of things. Most of it is just null bytes. All these zeros are null bytes. I think we can also hide null bytes. So it will hide everything that is not actual information. And then you can see there is something that looks sensible. Yeah, create table oranges, and then there is more stuff, and we have some data here that is stored in some format that we don't know. Oranges, apples, and then there is more stuff at the bottom. Right. Let's, I think, let's keep the null bytes hidden. Now, there is a slight issue with this. The issue is that this editor is trying to parse everything with in fixed length bytes. So I think it assumes um, 8 bits or 4 bits in every byte or 8 bits in every. I know how it is trying to do that, but that is causing some problems because we also have things that are just 2 bytes, right? And we have things that span multiple bytes. So there is some structure, there is a method of storage that we need to understand before we can begin to make sense of these bytes. And for that, we can utilize something in this editor. Let's change to, okay, it is already big Indian and we are looking at decimal. Change that to hexadecimal. Actually, let's keep that decimal. I'll make a bit more sense. So let's open templates folder. There is nothing in our templates folder. So we'll create a new template, and templates are just simple scripts that you can write in TCL. Don't worry about the language, and sort of give this data some structure, so to speak. It is easy, and I'm going to do that right now. Let me open Vim side by side. Let me put this here. And what we're going to do is, first of all, we need to tell this the data is in big Indian. So big Indian, and then first 16 bytes, I think. First, yeah, offset 0 and 16 bytes are just this header string, right? So we'll say string 16, and we'll just say UTF-8 encoding, and this is our magic header. This is just labeled. It can be anything, does not have to be magic header. It can say anything. Then we have 2 bytes. That is our page size. And what is that? 16 to 18, and then rest of the, we can consume everything else and say 82 bytes are just, we don't care about the rest of the header. Right? Let's save this. Save this to our templates directory. I know where this location is. Not giving me anything. Oh, so it is inside the application support folder. Let me save this to desktop and I'll drag it over to desktop SQLite TCL. Let me drag it over SQLite.tcl, and we should see it. Okay, there. Okay, my bad, not Indian. Right? Let's refresh. Oh, I'm editing this. Let's edit this one, right? In application support com ready fields fish. And let's also close this one. We don't care about that. So, sorry. Big Indian. Refresh. Okay, so we have something. Magic header. So as you can see, if I click on that, it understands the magic header now. And if I click on page size, it understands that. So it is reading 2 bytes. And if I can double click on that, you can see it says 4096. So that is the size of our page in this database, right? Similarly, we can write a bunch of other stuff, and I think we can go ahead and also explore pages right away. So if I make more changes to the script, let's say, let's go back to this. So this is a database header format. We consume the first 100 bytes, right? Then what comes after that? Free list B-tree pages. Okay, so now we are on the page boundary. Well, we are already inside the page, but this is the first page, so there is an exception. Let's look at this one now. B-tree algorithm provides key value storage. Okay. Is there anything about page header? Number of keys, only exception. Okay, define depth of the leaf B-tree in an interior B page. B-tree page is, yeah, I know it can be either of that. Each entry in a table B-tree consists of 64 bits signed integer key and up to this many bytes of arbitrary data. Okay, each entry define the payload of a cell to be an arbitrary length section. For an index B-tree, the key is always arbitrary in length, and hence the payload is the key. There are no... Oh, okay. I will get to that in a bit. When the size of the payload of the cell exceeds, then will overflow. Okay, I know about that also. Oh, there is some information. So the 100 bytes database file header found on page 1 only, 8 or 12 bytes B-tree page header. Now, this is what we are interested in. So we are at B-tree page header. B-tree page header format is this. We have at offset 0, we have 1 byte, and 1 byte flag at offset 0 indicates the B-tree page type. So if we read that, it will tell us the kind of page this is, right? The value can either be 2, 5, 10, or 13. And depending on that, we'll get to know about the rest of the values in this header. So let's do that. So there is 1 byte at offset 0, then there are 2 byte integer at offset 1 to give the start of first free block on the page, or is 0 if there are no free blocks. Then there are 2 more bytes at offset 3 is the number of cells on the page. So this actually is what we are going to need because we want to know how many cells are there in that page. That is essentially our number of rows. Then there are 2 bytes integers at offset 5 designated start of cell content area. Okay. Fragmented 3 bytes and 4 byte page number at offset 8 is the rightmost pointer. This value appears in the header of interior B-tree pages only and is omitted from all the pages. Okay, in our case we are on a leaf page, so this I don't think is going to be there. So all right, let's see. 1 is the type, then 2, 2, 2, and 1. This is free block, number of cells, start of content area, fragmented 3 bytes. All right, let's put all of this information in our script and see what happens. All right. So there is 1 byte that says this is a page type. There are 2 bytes that are free block start, and there are 2 bytes that are number of cells. Then there are 2 more bytes, I think, for content area. Yeah, right. I think there was 1 more byte that was supposed to be. So we are at 1, 2, 2, 2, 1, and 4. 1, 2, 2, 2, and 1. And we are not going to find this one, so we can note this. So I'll just read 1, and that will give us fragmented 3 bytes. So let's read another one. 3 bytes, right? If I save this and refresh, All right, so we have a bunch of stuff. This is a page type. Page type says 13 at the bottom here. And 13 means this is a leaf table B-tree page. Then we have free block start. It says 0 or 0 if there are no free blocks. So we don't have any free block. Then it says number of cells is 3, right? 3. That means we have 3 rows in this table. Content area is at position 3779. If we go to this offset, we'll find something there. And 3 bytes 0. So there are 0 fragmented 3 bytes, right? This, by the way, is a really quick way to understand any binary data structure before you begin writing code. Just to develop some confidence and also just generally understand what you're getting into. You don't necessarily need to do this for well, even in this case, even for SQLite challenge, you can just jump into code and try and figure things out. But it helps to know where things are, generally speaking, and build that mental model. Right. Again, we can extend this to also visit our rows, because now we know there are these many number of rows, number of cells. We can visit all of this and at least put a marker at each position, each one of these 3 positions. That way we'll know, okay, when we click on that, it will take us to that position, right? Actually, let's do that. So we need a loop. Actually, we need to capture the number of cells. So we'll say set num cells to 2 bytes, and we are not going to need this. I think we can still show this label, so we can say entry num. We already had that level, number of cells to num cells. And now we have the value of the number of cells in a variable, so we can loop. We can say in a for loop. I think this is the syntax. Sorry, it's been a while. I think this is how you do it. Anyway, let's do it. If it turns out to be wrong, then I'll go and look it up. If while I is less than the number of cells, we want to increment I. Again, if it is highlighting everything, Vim is highlighting things for me, so I'm kind of confident it is going to work. If it doesn't work, then we can always go and look at the reference manual. Right, so we are at this position. It says number of cells. Sorry, we are after the header now, so that means we are at the beginning of the cells pointer, right? Again, what are cell pointers? Cell pointer array of B-tree page is followed by B-tree page header. Let k be the number of cells on the B-tree. The cell pointer array consists of k 2-byte integer offsets, right? So for every cell, we have a 2-byte integer offsets to the cell content. The cell pointer arranged in key order with leftmost cell, the cell with the smallest key first, and the rightmost cell, the cell with the largest key last. Right, and then cell content is stored elsewhere, so we'll come to that. Now, what do we need to do? We need to read 2 bytes. So we'll say set cell pointer to 2 bytes, and since this is going to move, every read operation is going to move the file pointer. We need to capture the current position so that we can come back to it and read the next two bytes. So we'll store old position to current position to this variable, and then we'll say go to cell pointer and say just this. We'll put a marker at that position, because again we don't understand the exact structure of that data cell, so we can't parse it. Well, if we write a lot of script and we write that whole program in TCL, then maybe we can. I just don't want to do that, so I'll just put a marker at the starting byte of our cell and say cell whatever I at location this. Cell pointer, right? And then we go back to read next 2 byte and do the same thing. So we'll say go to hold position, hold. Okay, let's fix that. Pause, hold, pause, right? Save this and refresh. Right. So as you can see, we have, it still says number of cells, but it is not able to highlight the data in this view, because now we are showing that from a variable instead of directly attributing it to those 2 bytes. That's fine. We still know this is the correct information because it says 3, right? 0003. That is 3 in hex. I mean, 3 in decimal is 3 in hex. This is our content area. It says 3779. Now these are 3 bytes, and this is what we're doing here. For every cell, we visited that offset and dropped a marker there. Cell 0 at location this, cell 1 at location this, cell 2 at location this, right? So this is what you're seeing. If you look at this, this is one cell. It says, so there is supposed to be some binary information here. It is not parsing all of that correctly, but after that you can say table apples, create table apples, ID, whatever it is, storing all of that information. So if you look at this much only, you'll see this is actually our page header. Where is that? This is a database header. Sorry, my mistake. I misspoke. That is not page header. This is record. It says, because we are in cell area now, it says table is the type of the record, right? So this type, let me rearrange this. Then there is name. It says name is apples. Then table name, again, it is going to be same because both of these things are same in our case, apples. Then we have root page. Well, root page is, where is it? Let's see. We are looking at a record, or what are we looking at? We are looking at a cell. There is some SQL. It says create table apples. Actually, let me try and highlight this. Create table apples, and then there is some other information here that is not being displayed. This space, it is actually, sorry, this thing that I'm highlighting, it says 2. That means root page 2. And then there is some SQL, right? Here is the SQL that is used to create the table. If you go to this one, then we can again see there is a space. It says 3. That means root page 3. And if you go to this one, then, oh boy, I think this, yeah, it says 4, right? So yeah, I think that's pretty good. And at least for me, I have that mental model of things where everything is and how am I supposed to navigate this. Let's rearrange this. right? Cool. So I guess we can go ahead and start making changes in our code. Let's do that. So we have we are going to get. So if we don't get something that we understand, if it is not a well-known command, then we'll assume it is a query and we'll deal with it. Right. Again, I'm going to copy all of this, and yeah, don't worry about code duplication just yet. We'll fix it. We'll fix it. I will refactor it. I'll create a ticket and tech it, and we'll get back to it eventually. I'll just say else, and there is one more else down here. So we'll remove that. What's the problem with it? There is no problem. So now skip the header section. So actually now we don't want to skip the header section. This is the database header, and it contains our page information. So we need to seek, we are going to seek to offset 16 and read this information, right? So let's say, actually, let's just change this to 16, remove the comment, and we'll say page sizes parse. Actually, it is, I don't think it is a variant. What is it? Yeah, just 2 bytes. So we'll load that from this database file dot read 2 bytes. Again, big Indian. So we have page size, and we also explode all of that. Table name is, I'll just split the command dot split on space, and take the last value. So that is our table name. Now we have the page size. We have page size, so we know which page we are interested in, and we can jump to that location, right? Okay, so let's skip the database header. So skip to 100. What is this crying about? Yeah. Page header parse database file. So we are parsing page header, then we are skipping the 8 bytes, right? And we are looking at cell pointers. And again, we are still in the first page. So this is going to be our schema information, right? Now we have, at this point, we have everything that we need. And I think I might also change the structure of this SQLite schema rows. We'll make it a dictionary. Why not? We'll say record. I think we'll use table name instead of name. So we'll use q.decode UTF-8 and put this in there. Cool. So now we have everything we need in this, and we can just look it up using name. Let's do that now. So we have our table name. Let's also strip that. Right. I'll call it table underscore info SQLite schema row table name. So we have the table info and our page number is table info root page. I think all of this is just bytes, so we'll probably have to decode root page. Parts record. If it is serial type, then we get an integer. Okay, yeah, I think we will get an integer back. That's fine. So we have the page number, right? Database file dot. Let's jump to that location. We have our page size and we have our page number. Page number multiplied by page size. We seek to that position. And here we have a page. So, again, standard stuff. We'll parse page header. And so this page header is also going to be what is this thing doing? Is it also seeking? Oh. I think read will advance the file pointer, so we don't need to worry about that. When we parse this, we are all there is this 100 plus 8. Why is that? Not sure. Let's put it to do here. I'll get back to this. Right. So actually, at this point, you can just copy paste a bunch of stuff and things will be fine. But we are not trying to read all of that data. We are just trying to figure out how many cells are there. So in page header, we already have number of cells. So we can just print that page header dot number of cells, and this should be fine, right? So we can try and execute this, give it a query, and see what happens. How was that? I think this. We'll give it, say, apples. It says 2. Okay, and let's give it oranges. It says 0, ORANGES, or is that sample.db? Huh. It says nothing. Why is there nothing? Can I? What? I think, do I have SQLite 3? Okay, we have ORANGES and apples. Select star from apples. 1, 2, 3, 4. Okay. So in apples there are 4. In oranges there are 1, 2, 3, 4, 5, 6. 6 rows. Okay. So what are we doing wrong? Let's try and fix this for apples, I think, and try to get to 4. Let's go back. Right. So what are we doing here? Database file dot seek 100 page header. Okay, we parse everything. So we found the page size. and page number and our table name. So our table name is apples, and for apples the page number is, what is this? This is 0f8f. What is 0f8f? I don't want to do maths. So this is our first page. This is our database header. This is our first page. On first page, we find apples and it says, go to this page, page 2, and you'll find something. So page 2 and our page size is 4096 multiplied by 2 is what? 8192. If we go to 8192, what do we see? What is this? We are somewhere in the neighborhood. 8166, 8196, 8192. All right, so this is where we are. Golden, delicious, yellow, Honeycrisp, blush, red. I don't know if those are actual. Golden, delicious, yellow, Honeycrisp, blush red, Fuji, Granny Smith. We should see all of this. Yeah, and we do see all of that. Okay. So there is a jump cut. Took me about 30 minutes to figure out what was wrong, and this is an off by one error. So the thing is, the pages are numbered beginning with 1, right? And here, we are not dealing with that. So what we need to do is, we need to say, subtract one page size from whatever that number is, because first page is at offset 0, right? So page 1 is at offset 0, and if the page size is, let's say, 1024, then the second page is at 1024, right? So page number 1, if you simply just multiply this, then the it will go to page 2 and treat that as page 1, and that is why we are getting wrong results. Right. And I had to pause the recording for a bit and figure this out. I did that eventually, and now it is working fine. Have a look at apples. It gives us 4. If you look at oranges, it gives us 6. Right. So it is working fine. All right. All right. Let's remove all this, all of this other information. And now we are ready to push our code. Let's do that. Cool. Stage 3 test passed. All right, all good. Let's see. Is it updating? Yeah, it is updating. So looks like I'm top. Count rows in a table completed. Read data from a single column. Now that you're comfortable with jumping across database pages, let's dig a little deeper and read data from rows in a table. Here's how the tester will execute your program. It will give us a query. Here's the output it expects. Okay, so again, I guess we'll just split this and pick the column name, something like that. The order of rows returned does not matter. Rows are stored on disk in record format, which is just an ordered sequence of values. To extract data for a single column, you'll need to know the order of the columns in the sequence. You'll need to pass the table's create table statement to do this. The create table statement is stored in SQLite schema tables, SQL column. Yeah, we saw that. All right, so this one. Not interested in implementing SQL parser from scratch. SQL parse is available as a dependency if you'd like to use it. Yeah, so we saw this import SQL parse available if you need it. What is this thing? SQL parse. SQL parse is non-validating SQL parser for Python. Okay. What does it do? Raw is this statement is SQL parse dot split. Raw statement is this, like start from what? Oh, so it can also tokenize, yeah. Pretty good, pretty good. What's the documentation? So we can split, we can format, we can parse, and parse will give us returns a tuple of statement instance. In most cases, there's no need to set the encoding parameter. All right. Okay. We can get back to this in a bit. For now, I think I'll just stop this video right here. Go and get some sleep because, yeah, that was a this was a difficult bug to catch. And I'll see you next video.